All right, everyone, welcome back. So in this lab 12, we are starting the sequence of what we call optics. So we're going to talk about light and interaction of light with different type of mediums. So we're going to start with lab 12, which is an index of refraction. Then we're going to talk about um, total internal reflection. Then we will see how the light interacts with mirrors and lenses. So that means, next few labs basically going to be in terms of interaction of light as it reflects and refracts off of different mediums. So in this lab 12, we're going to basically start like introduction. So I'm going to give you sort of introductory, the theory, and we will be then continuing with that uh, at least next several labs. All right, so let's talk about then in terms of this index of refraction. So we're going to talk about how light, okay, so is what we call electromagnetic radiation or electromagnetic wave. That means it moves in free space, right? In vacuum, at the speed of light, that is c is equals to 3 times 10 to the 8 meters per second. So this is the speed of light in vacuum. And because it's a wave, even though it's an electromagnetic wave, it you can use most of the wave properties of that you learn about mechanical waves, right? Pretty much can be applied here as well for electromagnetic wave. That means you can find the wavelength and the frequency, and product of wavelength and frequency is what you will have pretty much for the speed. That means wavelength of the light in vacuum times its frequency, you will get then this number 3 times 10 to the 8 meter per second. Now, um, if you look at this wave model, that means you can say that in terms of the light, you can look at it in terms of like a wave like this, and exactly right. So this is the wavelength here, and then you have the frequency, which is oscillation per second. And this model is very useful, for a lot of applications like diffraction, interference and things like that. But one thing we will see is that next several labs, we're going to be using a different model for light, and that's going to be a ray model, which instead of talking about a wave kind of like moving like that, we can say that wave is moving like a sort of like in a straight line. Okay, so this is sort of like, let's say, simple model that we can use for light, that is very useful for lenses and mirrors, and whenever light is going from one medium to another, because it allows us to easily see how the light, let's say, changes direction. So when it bends going from one medium to another. So using the ray model of light allows us to use geometrical properties of light and get some of the answers, rather, quickly. So in terms of then, let's say for the light, you can always think of, let's say, that light has um, some kind of origin, right? So it has to start from somewhere. So we have always an object or the light source, and so let's say here's a source of light. So then the source always radiates the light, and generally we can think of, like, let's say this radiated light moves like this, like a wave, if you look at it as in terms of wave like that. So it moves like this, with the wavelength and frequency and all of those things, and it kind of radiates away from a source. So now what I can do here is I can pretty much represent the same thing with the ray model, where I can say that, here go, the light is basically moving in that direction. Okay, so I can represent it with an arrow and a straight line, which kind of, very similar to that. And we can use what we call wave fronts, where this green lights, the green line represents the crest of those waves. Okay, so, right, so those green lines. So that means those lines are the wave fronts. And in terms of then um, the halfway between them is then, you can take like, let's say the trough, right? So those are the crests, and then halfway between those green lines is the trough. And put here, so we have wave fronts. In terms of then what we have here is, we can always assume that whenever the light going through that wavefront, it always has to be perpendicular to that. So that means it's easy to use sort of like this geometrical approach to look at the light. So that means you have those wavefronts, and then you can draw those ray diagrams, right? Those ray light that are perpendicular to those wavefronts. Now, in terms of then, if you look at some kind of source that is very, very far away, then you can, in a way, assume that if you, think like this, if you kind of continue that what we have, this wavefront's going to go like this and eventually kind of become, pretty much parallel to one another. So for example, for a source really far away, I can think of like, let's say those wavefronts pretty much are like this. So then the ray diagram, the rays, right, will be like that. So like parallel to one another, since the wavefronts are parallel to one another. Remember, they always have to be parallel to one another, like this. And I can then assume that if I see the rays, so let's say here you have ray 1, ray 2, and ray 3, right? If they are coming from a light source and they are parallel to one another, that means we can assume always that light source is far away. Okay. And instead of looking at 3, 4, 5 light rays, I can just look at one of them, because you can see, right, second one is parallel to the first one, the third one is parallel to the second one and the first one. That means they're all kind of going to be behaving same way as just, let's say ray 1. So that's why one of the things we will see that a lot of times for this lab and the next lab, let's say, we can just use one ray instead of, let's say, 10, 15, and things like that. So we can just use one and generalize it and say that all of the other ones basically behave just like this one. Okay, so one thing we have here is this. So let's say here's a boundary between two mediums. So this boundary basically separates the medium on the left side with the medium on the right side, and means that they're sort of like, let's say, different material, different density mediums. So let's say, let me call this is boundary line. Okay, and this is medium 1, and this is medium 2. So, and in terms of then from medium 1, medium 2, right? So you have two different materials, two different density, and light then goes from one medium to another one. Let's assume, for example, medium 1 is air. So I can say this is air, and medium 2 is, for example, it can be water, or can be glass, right? So something that has different density. Okay. One of the things we can do, we can always assume that vacuum and air always have sort of like same properties. That means in terms of air or vacuum, a lot of times we can treat them as basically the same. Okay. The difference between air and vacuum is very small. So let's say medium 1, when we say air, in a way it would have been exactly same up to, let's say, 3 or 4 decimal points, right, for us, as it, let's say if it was a vacuum. So air or vacuum, you can say can always be treated as the same medium. Again, let's say the first medium is air or vacuum. Second medium is something like more dense, like water or glass or something like that. So now imagine then you have a light. There is incident. So let's say here's a light coming in, and it is moving toward this medium, the line that separates medium 1 and medium 2, the boundary line. Okay, that means beyond that point, to the right of that point, is second medium. When the light hits the medium or the boundary line, then two things will happen. Some of the light will be reflected. So this is what we call incident light. So some of the light will be reflected. So let me kind of do it like this. So this is then going to be reflected. This is the reflected light. That means fraction of the light will be reflected. But then if the medium 2, let's say, allows the light to propagate to other side, then we will also get what we call refraction. That means some of the light will go to the other side, and this will be then a refracted light. So this is incident light, then you get a reflected light back in the same medium one, and then some of the light would then be refracted or propagate to the other side. That's medium 2. Okay. Now, in terms of when this happens, right? So you can see right now we have three things: incident light, reflected light, refracted light. But looking at this, one thing we can always, experimentally measure is that when the light goes from one medium to another, it always changes its speed. So since medium one is vacuum or air, I can assume that velocity or the speed of medium one is same as speed of light in vacuum, right? It's c. Now velocity two, which is the medium two, uh, well, medium two is more dense. That means the light has to interact with more particles. So, and which means that the light will then slow down. So one of the things we can do here is we can assume that when the light goes from, let's say, less dense medium to a more dense medium, it will always slow down. Okay, so that means V2 will be less than V1. Okay, because it's more dense material, so the light will actually, in this case, slow down. Okay, so that's one of the important things that happens to the light. It slows down when it goes from one medium to another. Another thing happening is that, which we can see from so like a different angle, right? So let's say now I'm going to draw the boundary line like this. I'm going to draw the boundary line like that. So here's, I'm going to say this is the medium 1, and this is going to be the medium 2. Okay. Now, the light also changes direction when it goes from one medium to another. So you can really see that in this specific diagram, because I draw this incident light such that it is perpendicular to the, let's say, to the surface. Okay. But one thing we do here is we always measure the direction of the light with respect to the normal line that is normal to the surface. And you can see that in this case, incident light is along that normal line. And whenever it is along that normal line, this is probably the only time you can think of is that it doesn't really change the direction. So it comes, hits the boundary line, and because it is parallel, right, along that, the normal line, so this is that normal line, it then goes without changing direction into the next medium. Okay. But if the light is incident, so let's say this is my normal line. Normal line is always perpendicular to the surface. If the light is incident to this normal line, such that it has some angle theta, it's not along that normal line, but it has a angle theta or relative to that normal line. So let me do it in terms of this. So let's say there's some angle theta with respect to that, which we can represent as theta 1. Then the light will change direction. Okay, that means imagine that this would have been its original path, right? This would have been its original path when it goes into the medium 2, but because medium 2 is more dense, let's say, for example, in this case we're going to assume it's more dense, then what will happen here is light will change its direction such that it will be moving straight line, so it will be moving closer to this normal line. That means it's going to bend toward the normal line. And then if I measure the angle uh, of the refracted light relative to the normal line, I can represent that angle as theta 2. Okay. Theta 2, then you can think of, like, let's say theta 1 is incident angle or angle of incidence, and theta 2 here is the refracted angle, sometimes known as a angle of refract. Okay. Now, one of the things we can see here is that in this particular case, um, we can see that light changes direction, and it changes direction relative to its original path. And the way it changes direction is when it goes from less dense to a more dense, it always bends toward the normal. Okay, it always bends toward the normal, and the theta 2 is always going to be less than theta 1. That means you can always assume, that means whenever you absorb the light, you know, when it's in, refracted light has a smaller angle than incident angle, you can always assume that it goes into more dense material. All right. Now, again, two things happening is light gonna change direction and it's gonna change its speed. That means I also have V2 and V1 like this. And again, in this case, what I will have is that V2 will also be less than V1. That means it's going to bend toward the normal, have a smaller angle relative to the normal, and slow down. Those two things are going to happen to the light when it goes from less dense into more dense medium. Now, those quantities are related to one another. So one thing I can do here is, if I look at by how much, let's say, uh, the velocity 2, which is the speed of light in medium 2, is, how much it changed relative to the speed of light in vacuum, for example. I want to know basically, you know I know what is the speed of light in vacuum, which is 3 times 10 to the 8 meter per second. Then let's say I want to know what is the speed over here in this new medium. Then that ratio of speed of light in this medium, this new medium, let's call this medium 2 in this case, right? This ratio is very important quantity. This ratio is defined as index of refraction. So n is the index of refraction, and it is defined as the ratio of the speed of light, which is kind of like a constant, right, divided by how fast the light is moving in this medium. That means in this case, I will say that this is basically, n2. N2 means that medium 2. Now, one thing I have here is that this n, again, so this is index of refraction. Pretty much defined as the ratio of the speed of light to the speed in this particular medium. So that's why if this is, for example, medium 1, then index of refraction medium 1 will be speed of light divided by velocity, or the speed of light in this medium 1. But remember, if I take medium 1 to be air or vacuum, then I can say it's speed of light in vacuum divided by speed in medium 1, which is also C, since it's air or vacuum. Then I'm going to get 1. Where then this 1 over here is basically the lowest you can have for the index of refraction, and that always represents air or vacuum. Okay, so index of refraction equals to 1 always represents air or vacuum. Okay, that because, so let's say you can think like, in terms of the velocity, right? So if you're comparing speed of light over the velocity in this particular medium, because this is same as speed of light over speed of light in vacuum gives you 1. Okay, and everywhere else, when it's more dense, even slightly more dense, the light will slow down. So then in the denominator, you're going to get a smaller number, and smaller number will give you higher index of refraction. That means this is one of the ways we can find index of refraction, where n is equals to c divided by velocity in this particular, particular medium. Okay, so but obviously, it's not easy for us to measure the velocities, right? So how the light is moving so really fast, so it's really difficult to measure the, let's say, the speed. One equation we know for the speed is the distance over time, but it's moving so fast, right? So our we don't have a clock that can measure the how fast the light is moving, let's say in 2 meters or 5 centimeter distance that, let's say, we can measure. Okay, so there's another way we can actually find the index of refraction, and that will be from the second condition, which is looking at the how the light changes direction. Because one of the things we have here is changing direction is much more noticeable, much more visible to us, and we can easily measure that angle using a protractor, for example. And those theta 2 and theta 1 are related to one another, and whenever the way they are related, they also related to the index of refraction of those mediums. Okay, so this comes down to what we call Snell's law. So the Snell's law basically tells us this: if you take incident light and measure its angle relative to the normal, and take the refracted light and measure its, let's say, angle relative to the normal, then those two quantities are related to one another. Remember, so one thing we have here is, if I have, this is my medium, right? Sorry, this is my the boundary line, and this is my medium 1, this is my medium 2. Remember, one of the important things I need to do here is draw a normal, okay, which will be perpendicular. And remember, what I have here is, then I have incident light. Let me try to draw a normal here. I mean the straight line. There you go. We can use this tool here. All right, so this will be then index, sorry, this will be then, let's say then my incident light. So then I can say that this is my theta 1. Okay. By the way, as I mentioned, right, some of the light will reflect back. And when it reflects back, the way it reflects is always going to, reflect exactly same angle as the incident angle. Okay, like this. So this is known as law of reflection, by the way. Law of reflection. And law of reflection tells you that theta 1 is always going to be same as, let's call this theta reflected. So theta reflected. That means incident angle and reflected angle always going to be exactly the same. All right, so now we don't really care at this point about reflected light, because a lot of times, let's say reflected light is, doesn't really help us unless it's a mirror, for example. But in this case, we have a propagation of light to the other side. And to see how it changes direction when it goes, let's say, to a different medium, which we can say right now, this is N1, index of refraction of medium 1, which again, it gives us an information, right? Because see, if N1 is equals to 1, that means I know that this medium here is air. Okay. So here I have N2, which is index of refraction of this medium 2. Now, the information, the value of index of refraction can give me information about what type of material I'm dealing with. And I know, right, this number cannot be less than 1. Again, index of refraction is 1 and above that. It's a number without any units, because, this is speed over speed, so the units cancel out. So it's just a number, but its number equals to 1 and anything greater than 1. All right, so which is kind of like a clue, right? So if you calculate index of refraction and you got smaller than 1, you probably did something wrong. So I know that this number is going to be greater than, let's say, greater than 1, because N1 is already 1. If you have N1 equals to 1, N2 equals to 1, that means there is no change in medium. The light is going to just go in, straight line. But because it's a different medium, light will change the direction. And when it does, if, because index of refraction of the medium 2 will be higher, it will then bend toward the normal. Let me do a different color. So it's going to go like this. Okay. So this will be then refracted light. And when I measure this theta 2, okay, I can then say that theta 2, theta 1, N1 and N2 are related to one another. Okay. And Snell's law basically relates those quantities. Okay. It relates those quantities where it says that sine of theta 1 over sine of theta 2 is equals to always to the ratio of the index of refraction. So it will be equals to the N2 divided by N1. So that means the ratio of sine of the angle 1 divided by sine of the angle 2, theta 2, equals to then N2 over N1. We usually rearrange this, but one of the things we're going to do in this particular lab is this. Then sine of theta 1 equals to N2 over N1, which is basically a constant, right? Doesn't matter how you change your thetas, this N2 over N1 will not change that constant. Then times, so like, let's say sine of theta 2. So what we're going to do, we're going to use this version of this equation. So technically, the Snell's law is written like this. N1 sine of theta 1 equals n2 sine of theta 2. Okay, but for us, this is actually the equation that we're going to be using to take an experimental data. Because one of the things we're going to do here is this. So it says that sine of theta 1 is proportional to sine of theta 2. That means they're not equal to one another, but they're proportional. If you increase, let's say 1, the other one is increases. If you decrease 1, the other one decreases. And one thing we have here is then this n2 over n1 is become basically a proportionality, sign, right? Proportionality factor. That means using this equation, right? Sine of theta 1 equals to n2 over n1 times sine of theta 2. We're going to use this equation where we're going to take experimental data of theta 1, which is basically we have incident light, we measure the angle theta, and then we measure theta, theta 2 for that. So let's say this will be in terms of, let's say, trial 1. Let's say, let me put it like this. So this is theta 1, measurement 1, I guess. Let's say things like this. So these are, let's say, measurement 1, right? So for theta 1, we have measurement 1, 2, 3, 4, 5. And then same way, then you get measurements for the theta 2. So then 1, 2, 3, 4, 5. Those are not angles. They're just basically measurements, right? That means for each theta 1, I get theta 2, right? That means, I can do those type of measurements. So that means, or thing like this. So let's say if I do it like that, right? Angle of incidence, and this one angle of refraction, like this. And then we get, trial 1, right? So theta 1, trial 1, theta 1, trial 2, theta 1, trial 3. Remember, theta 1 means theta for the incident angle, right? Medium 1. So theta 1, trial 4, and that. Same way we get then theta 2 for, in trial 1, theta 2, trial 2, theta 2, trial 3, theta 3, trial 3, and that. Okay. But we can see that in this equation, thetas are not the ones that are related to one another. They're sine of, those angles are. That means we need to then have two more data, two more columns, sine of theta 1, and take this one to be sine of theta 1, trial 1, sine of theta 1, trial 2, and that. And then here we're going to have sine of theta 2. So then this will be sine of theta 2, trial 1, sine of theta 2, trial 2, sine of theta 2, trial 3, right? And so on and so forth. That means we're going to have the experimental data like that, where then using sine of theta 1 and sine of theta 2 experimental columns, right? We can then plot them. So if I plot those, that means if you plot sine of theta 1 relative to sine of theta 2, that means, plotting those, you can see, right? My y-axis is the sine of theta 1. My x-axis is the sine of theta 2. So that means if I have this sine of theta 1 equals n2 over n1, then sine of theta 2, I'm going to be able to see that sine of theta 1 and sine of theta 2 are, proportional, linearly proportional to one another. So this is like basically same as y equals mx, where theta 1, sine of theta 1 is y, sine of theta 2 is x. Then if I take those data points and, use then the, find the best fit line, use the curve, curve fit, then I can see that the slope of this guy, this graph, is then equals to n2 over n1. That means I can then use this to get, this ratio of n2 over n1. Our goal will be this. We don't know what second medium is, but taking data of the angle of theta 1 and theta 2, right? We can use this graph then to find a quantity that relates those. That means what we're doing here is we're finding the slope, where the slope is equals to then n2 over n1. Then think like this. If I have given you already what n1 is, then you can use the slope to find what value of n2 is. Because remember, n1 is just air. and you know what the value of N1 is because it's air, right? N1 is always equals to 1 because it's air or vacuum. And that's what we're going to be doing here in this lab. So that means our goal will be to find the index of refraction of the medium 2, where the light refracts. Okay, so let's look at then the experiment itself. Okay. Here's the experiment. So you can see, right, we have a video of light passing into acrylic, so acrylic glass, and using the provided kit to analyze lens focal, basically find the index of refraction of that. Okay. So here's an experimental setup. So we have a laser, and our acrylic glass is this one over here. So you can see, right, this is the acrylic glass. That's the acrylic glass. Okay. Then what I have here is this will be then the normal to the boundary line. So this is basically my boundary line. This is going to be the boundary line. You can see, right, then you have a green laser. This is the boundary line, and the red here is the normal. Right. So this is your normal line. Then what you have here is that this is then your theta 1, and this is here your theta 2. That means you have your incident angle and you have a refracted angle. So you can see, right, you can't even see the reflected. If you really look at it, you can probably see it somewhere over there, but we don't really care about that for this particular lab. So we only care about normal the incident light and the refracted light, theta 1 and theta 2. That means hopefully you should be able to see from here what is the angle of incidence, okay, or the incident angle. So basically look at it from here and be able to measure. And that's starting from this as a reference position, right, 0. You can see, right, this pretty much where you get the angle for the angle of incidence. And then this one relative to the normal again, where you get your refracted angle. Okay, so it should be relatively straightforward, right? So you get a protractor as a tool, and you should be able to use that to get the angle here. And this is sort of preliminary that allows you to kind of get some of those values. Now, you can see, right, so you have those. Also pay attention that you have 2 submissions. So if you get wrong first time, try again, and hopefully second time you get it right. Okay. So from here, basically, this is our experiment. All right, so technically you can just go from here when it's perpendicular, right? So that means it's perpendicular to the boundary line, or let's say you can use this tool over here, right? So pretty much if you put it like that, just make sure that you start when it's let's say parallel to that, which gives you the angle of 0. Okay, that means what you will see here from here, the laser kind of like goes to the right like this, all the way to like almost 75 70 degrees or so, and then comes back and goes to the left side. Now you don't have to measure both right side and the left side. Measure either right side or the left side. That means what we're going to do here is we're going to measure from, you can see, right, let's say from here, right, from 0 to about 70 degrees, and then you stop, or from here, right, let's say start from here if you want, then go all the way to 70 degrees to the about other side. But that's it, either right side or the left side, not both. That means, for example, if you go here and start from here, right, then you can see that light right now is pretty much comes from like this. So it's parallel to the normal. Okay, that means that's your first measurement will be 0 for the theta 1, and it's 0 for the theta 2 as well. Okay, so it's pretty much 0 0 for the theta 1 and theta 2. But then what you're going to do here is you're going to make a measurements of every then 5 degrees. So 5, 10, 15, 20, 25, 30, 35, 40, 45, and you're going to go all the way to about 70 degrees. Okay, that means what you're going to do about, you're going to have like about 15 or so measurements. Okay, so and that means every 5 degree for the incident light, measure the refracted light. Okay, that means make sure that you get all the data points, because sometimes students don't take all the data points. So make sure you go 5-degree increments, and all the way from 0 to about 70 degrees. Okay, I don't think it reaches 75, but it does reach, I think, 70 degrees. So you should be able to do that. Okay, so then pretty much answer some of those questions. In terms of then what we have here is let's say this, you're gonna let's say answer some questions over here, log this, and come back, and you basically have the same thing. So same experiment, right? So here then you're going to collect data. So you can see, right, I'm pretty much give you everything in terms of 45, but you can continue from that. And then you have angle of refraction, then you have sine of I, which is incident, and sine of R, which is refracted. That means you're going to continue and go all the way to about 70 degrees. So that means make sure that you have increments of 5 and go all the way to your last measurement you can see when it goes pretty much clockwise from 0. Because from here then you can do your experimental measurement, right? So here you don't have data, but for example, once you populate this column for the angle of refraction as well, okay? So for example, let's say I'm going to just make up some numbers. These are just uh, made up numbers. Do not use them except the 0. It will be 0 0. So let's say this is 2, this is 4, this is 5, let's say 6 or something like that, right? So you can see, right, already you get then sine of theta I, sine of theta R. And if I come back, you can see I already have a data. So once you get then the curve, you should be able to use proportionality curve, or linear, and then from here you can get the slope and everything like that. Once you get the slope, once you get basically all the data points and get the slope, as I mentioned, right, you should be able to use the slope to get the index of refraction of this glass. That means, our goal here is this: what is the integral index of refraction of this acrylic? Okay. Once you experimentally determine the value of the index of refraction of the acrylic, then you're going to be given the accepted value, or the theoretical value of that. Then do a percent error to see if your experiment is let's say successful or not. And remember, that's going to be then accepted minus experimental divided by accepted, then times 100%. That's the equation for the index of refraction, percent error of the index of refraction, right? The difference between accepted and experimental. You can use absolute value to make sure you don't get a negative. Divided by the accepted times 100, then that will give you your percent error. And hopefully you will get under 10%. So margin of error for this lab will be at 10%. So successful experiment will be if you get under 10%. All right, guys, so that's it for this lab.